Let's look at Coulomb's law, which is very similar to Newton's law of gravitation, but describes the electric force between 2-point charges, and we treat these charges as particles which have a very small mass and a negligible size. Now the magnitude of this electrostatic force between these 2-point charges is given by Coulomb's law. So we can write the magnitude of the electrostatic force between charges A and B as a constant multiplied by the magnitude of charge A and the magnitude of charge B over the square of the magnitude of the radial vector between them. So therefore, in vector form, we can write the Coulomb force as K by QA by QB over R squared in the direction of R on the magnitude of R. Okay, so this here is the unit vector, or the direction vector in the direction from A to B. So therefore in vector form, we can write this as R cubed in the denominator here, which is the vector form of Coulomb's law. Now the constant K is equal to 8.988 by 10 to the 9 Newton meters squared per Coulomb squared. And if you recall the elementary charge of an electron, which was 1.602 by 10 to the minus 19 coulombs, well, 1 coulomb is then really a massive amount of charge, isn't it? Now alternatively, we can write the magnitude of the electrostatic force as 1 over 4 pi by epsilon naught by the magnitude of charges over the square of the magnitude of the radial vector. And epsilon naught is then 8.854 coulombs squared per Newton meter squared. And that just simply comes from Coulomb's constant. But this epsilon naught is called the vacuum permittivity, and it's practically the capability of an electric field to pass through a vacuum. And we'll revisit this quantity when we look at capacitors and dielectrics to make more sense of it. And I encourage you to really verify this unit. So we know charges are in coulombs and R squared is in meters squared. So from that you can get the units of this constant because the force is in newtons. And the same thing can be done for epsilon naught. So if we look at the mass of a proton, so that's equal to 1.673 by 10 to the negative 27 kilograms. And the mass of an electron is 9.109 by 10 to the negative 31 kilos. And the elementary charge, which is the magnitude of the charge of an electron, is given here. And if you recall Newton's law of gravitation, which describes the magnitude of the gravitational force between 2-point masses A and B, so we have the gravitational constant by MA by MB on the square of the radial distance between them. So you can really see the analogies between Coulomb's electrostatic force and Newton's law of gravitation. And recalling that the gravitational constant is 6.674 by 10 to the minus 11 Newton meters squared per kilogram squared. So from that we can substitute the mass of the proton and the electron and the elementary charge of the proton and electron, and we'll take the magnitude of the charge, so ignoring the sign for now. So what we have effectively, if we divide the magnitude of the electric force on the gravitational force, well, that gives you 2.269 by 10 to the 39. So you can see how much larger the electric force is compared to the gravitational force. And as we've mentioned previously, opposite charges attract, whereas like charges, so positive to positive, repel each other. And I'll see you in the next video.